Hi, I am Muhammad Ali Javidian from University of South Carolina. Today, I will talk about this work on Markov blankets in chain graphs. This is a joint work with Marco Altorta and Puyan Jamshidi. Chain graphs are a type of mixed graphs that may have both directed and undirected edges. However, in a chain graph, there is no partially directed cycle. For example, in the figure at the left, there is a partially directed cycle, which is U, Z, V, U. So this graph is not a chain graph. On the other hand, the graph at the right is a chain graph. There are at least 3 different interpretations of chain graphs. But in this work, we focus on the chain graphs under the Loritzen, Vermuth, and Friedenberg interpretation, or simply LWF chain graphs. There are some concepts and notions that have been extensively studied in the literature of probabilistic graphical models and causal inference. However, they are absent in the context of chain graphs. One of the most important concepts in the case of directed acyclic graphs, or DAGs, is Markov blanket. The Markov blanket of a target variable t in a DAG is defined as the set of parents, children, and spouses of T. The format of an spouse is an induced V structure, like TKL. So L is an spouse of T. Since Markov blankets take advantage of local computations, they can be used as a powerful tool for learning tasks, in particular for causal structure learning. Now we are ready to talk about our first contribution in this work, which is the graphical characterization of Markov blankets in LWF chain graphs. The Markov blanket of a target variable t in an LWF chain graph consists of the set of parents, children, neighbors, and complex spouses of t. The format of a complex is an induced U structure like H, I, J, K, T. So H is a complex spouse of T. To show that our characterization of Markov blankets in chain graphs is correct, we proved that Markov blanket of target variable T in an LWF chain graph probabilistically shields T from the rest of variables. And then we proved that a standard Markov blanket discovery algorithms like Gaussian incremental association Markov blanket and its variants are still sound algorithms for Markov blanket discovery in LWF chain graphs under the same assumptions. The characterization of Markov blankets in chain graphs enables us to design new algorithms for Markov blanket discovery in chain graphs. For this purpose, we designed an algorithm that has 2 phases, the grow phase and the shrink phase. The main difference between this algorithm and others for Markov blanket discovery in chain graphs is in its grow phase. More specifically, this phase has design based on LWF chain graphs characterizations. That is, the algorithm first recovers the adjacents of T, which means the set of children, parents, and neighbors of T. And then the algorithm recovers those nodes that are outside of the adjacents of T, but they belong to the Markov blanket of T. However, as you can see in the figure, it's quite possible that some extra variables fall in the Markov blanket of T. In the second phase, or the shrink phase, the algorithm discards false positives from the Markov blanket of T to obtain the true Markov blanket. Such Markov blanket recovery algorithms enable us to develop new scalable algorithms for learning chain graphs, exploiting locality in structure discovery. Now we extend discussed Markov blanket discovery algorithms to an algorithm for learning LWF chain graphs. This algorithm has 4 main phases. In phase 1, we recover the Markov blankets of all variables. In phase 2, we construct a superskeleton by connecting each variable to its Markov blankets members. In phase 3, We remove spurious links to obtain the true skeleton. And finally, we orient edges to recover minimal complexes. Note that any sound algorithm for Markov blanket discovery in LWF chain graphs can be used in the first phase of this algorithm. In order to evaluate our algorithm empirically, we compared the performance of our proposed algorithm with 6 different Markov blanket recovery algorithms against the state-of-the-art algorithm for learning LWF chain graphs, which is LCD algorithm. In our experiments, while our Markov blanket-based algorithms have better precision, the LCD algorithm enjoys a slightly better recall. A possible explanation is that the faithfulness assumption makes the LCD algorithm overconfident and aggressive. Whereas under this assumption, our Markov blanket-based algorithms are more cautious and, more importantly, more precise than the LCD algorithm. Another important thing that I want to emphasize here is that Markov blankets of different variables can be learned simultaneously and independently of each other. This allows us for parallel computation for scaling up the task of learning chain graphs in big data. As a summary, first, we provided a graphical characterization of Markov blankets in LWF chain graphs, and then we proved that some of standard algorithms for Markov blanket discovery in DAGs are valid algorithms for Markov blanket discovery in chain graphs. The characterization of Markov blankets in chain graphs, along with our theoretical results, enable us to design a new sound algorithm for Markov blanket recovery in LWF chain graphs. Taking advantage of local computations help us to finally extend Markov blanket discovery algorithms to an scalable algorithm for global structure recovery in chain graphs. One natural direction of this work could be the extension of characterization of Markov blankets for other type of chain graphs. All code, data, and supplementary materials are available at the following link. Thank you.